Hi guys, today I'm going to present my research project, a novel deep learning model to predict lung cancer recurrence. Let's start off from the background. Lung cancer is a malignancy originating from uncontrolled cell growth of aberrant cells in lungs, and it is a critical health concern because it brings a lot of symptoms like cough, chest pain, and difficulty breathing. And it remains a serious problem because the survival rates have remained very low. The 5-year survival rate for small cell lung cancer is only 7%, and the 10-year survival rate is only a little above 1%. And almost all patients report having symptoms that affect their quality of life, including fatigue, losing appetite, respiratory problems, and cough and pain. Here is the traditional TNM staging system we use for lung cancer, and the TNM stands for tumor, nodes, and metastases that are present in the lungs. And as we can see, the later we move on to the stages, the lower the survival rates will be, and it can reach almost 80% of death rate. So since it remains a huge problem, I came up with this method to utilize deep learning to predict lung cancer recurrence. We want to prevent the recurrence of lung cancer early by utilizing the modern technology. And my study will consist of 2 independent models. First is the IDLE model. It utilizes the NLSC data, which is the National Lung Screening Trial. It is a website online, and it has free public available resources. And it focuses on HE images. And all of these images contain a pathologist's annotated regions of interest, which are abbreviated by ROIs. They are categorized into tumor, pre-malignant, and non-tumor areas. These tissue characteristics will be extracted by the pathologist, and these variables will be created for tumor classification. Preoperative manipulations included standardizing CT scanner parameters and processing LD-CT images. Tumor segmentation, intensity normalization, and feature extraction were performed across various volumes of interest, and a multi-layer perceptual network will be employed for predictive modeling, generating the IDLE score using cross-validation techniques. And from this graph, we can see the whole process being compressed into a flowchart. So both the HE images and LD-CT images will contain pre-annotated parts that will be automatically extracted by the deep learning model I created, and they will serve as preoperative variables to be put into this multi-layer perceptual network. After the steps in the deep learning model, it will then utilize a leave one patient out validation to calculate the IDLE score, which is specifically useful for this case because every time it's going to train using all the data sets and leave one out and use it as the test set and repeat it over and over again until all of the data sets are used. It increases the generalization and improves the overall performance of the model. And from here, the results we can see, the regions on the curve, the AUC score we generated are well above the traditional TNM staging, which means that utilizing this model, we can achieve a way higher accuracy of predicting lung cancer recurrence than the traditional methods without it. The second method is the COXNet. It is using the module segmentations from CT images that are processed to obtain masks, and radiomic features will be extracted. Multi-model fusion for recurrence prediction will be explored using pre-computed features due to dataset size limitations. One important thing I used in here is the survival analysis. It focuses on the survival probability and hazard probability. And then it employed the Cox proportional hazards model with elastic net regularization. And the performance will be assessed through k-fold cross-validation with a COXNet model tailored to the training set for recurrence prediction. And here is another flowchart for how this machine works. It will be consisted of multiple layers as well, from max pooling 3D, leaky ReLU, the activation function, and the convolution 3D. After all these, they will be flattened, danced, and activated again for calculation purpose. And after all, it will be applied through the COX layer for a survival analysis. And the dataset I used was from the NSCLC radiogenomics dataset that comprises of 211 patients with complete CT imaging, gene expression, and recurrence data available for 130 individuals. All of these will be processed to derive module masks and generating 107-dimensional pyradiomic features and 1,024-dimensional DenseNet features, capturing the texture and intensity patterns for lung modules and surrounding tissues. Here are the results for this one. It utilizes a k-fold validation, and the k-value here is 5. We divide the sets into 5 folds, and every time we use the previous 4 folds as a training set and the last one as the test set. And as we see as we move on to the later sets, the number keeps increasing and increasing. So the accuracy by plugging in more folds and more data, we will get a better result. And we will achieve almost the maximum result at the fold 4, and sometimes it decreases at fold 5, and it's probably because of over-linearization and too much generalization, which is what we want to avoid in the future. Okay, so here are 2 examples of the lung heat maps that we utilized. It is very important because certain features are extracted by the model's judgment of their importance and calculated outputs. What will be done in the future is that because of a limitation of this study, the sample size was comparatively small. So finding better datasets and larger datasets that fit this model will be able to perform for better results. And also additional prospective validation is required. Also, transfer learning from single modality datasets could aid in the training of multi-model fusion networks. So this is an intriguing area for future study because the more types of data we use, the more generalization we will get and the more overall ability to predict lung cancer recurrence and a higher accuracy in real life will be achieved. So, in conclusion, this study utilized a deep learning model to predict lung cancer progression in hundreds of patients. And after all the model developments, we can see they are all superior than the traditional methods, and they may be able to be applied in real clinical situations in the future. Thank you.